Now let's solve the same problem using the equations. I put yellow circles around V0, Vf, and delta T. Those are the given quantities. And I've listed the equations. Okay, now let's talk a minute about the equations before I get into the circling. This first equation is just what? Delta S is V0 plus V0 over 2 times delta T. If you're practiced in the reasoning that we use here, we see that Vf plus V0 over 2 is just average velocity, and we recognize that. Now, that's the average velocity, the average of the initial and final velocities, and when we multiply that by delta T, we get delta S. So what is this? This is just a rearrangement of what we get from the definition of average velocity, which is, if we go through the process, that the average velocity is delta S divided by delta T. So here's average velocity. If we divide both sides by delta T, we have the definition of average velocity, and we've used the property of the straight line V versus T graph, which is that we can average Vf and V0 over 2 to get the average velocity. Okay. The second equation, Vf equals V0 plus A delta T. That's not as closely related to the definition of average acceleration as this is to the definition of average velocity and the straight line property, but it's still quite closely related. If we were to subtract V0 from both sides, we'd have Vf minus V0 over here. That's the change in velocity. And that would be equal to acceleration times delta T. If we divide both sides by delta T, we find that the acceleration then is the change in velocity divided by delta T. So this is just a rearrangement of average acceleration, well, and in this case with uniform acceleration, straight line graph. Acceleration is delta V over delta T. This is just a rearrangement of that, where delta V is Vf minus V0. So that is very straightforward. So what we have here is just exactly what we get from the definitions of average velocity and average acceleration, and the fact that we have a straight line graph. These two equations are obtained by treating the first two equations as two simultaneous equations in the two unknowns, and the unknowns we could regard as delta T and Vf. So that if we regard these as simultaneous equations and eliminate Vf between the two equations, which is quite easy to do, Vf is V0 plus A delta T, so we can replace Vf here with V0 plus A delta T, and then we just simplify the algebra, and we end up with this third equation, and you're welcome to do that. Okay, and then down here, we eliminate delta T between the two equations. We could solve for delta T in either equation, probably easier here. We're going to get Vf minus V0 over A. You can verify that. And we plug that in for delta T here, Vf minus V0 over A, and then we multiply things out and rearrange it, and we end up with the fourth equation. Vf squared equals V0 squared plus 2A delta S. So these two equations come from everything that we know. They come from the definitions. They can be traced back to the definitions. But you're probably not going to want to rederive them every time you need them. So we write them down as two equations, and we pretty much memorize them. Now, there isn't a whole lot you can do down here to make much more sense of the equation than what you see here. You could trace it back to how the meanings relate to the meanings here, but that gets a little complicated. Most people are not going to be able to do that, and even those who would be able to do that are not going to want to invest the time and effort in doing it, and I wouldn't recommend that you do. It's just hard to understand that. If you do, that's a real feather in your cap. That's great. Very unusual that anybody would and could do that. Okay, so don't feel bad if you don't understand all the details of what this equation is telling you, but we are going to use it in ways a little later in terms of the definition of work and energy to make a lot of sense out of some things that we can observe out here in the real world, and some things that kind of escaped Newton, even though he pretty much had this whole scheme. He didn't have the idea of work and energy. Okay, this equation does make some sense. V naught delta t is how far you would go, or what your displacement would be if your velocity didn't change. Okay, because if the velocity doesn't change, then V naught is equal to Vf is equal to your average velocity, and V naught is equal to the average velocity, so multiplying it by delta t just gives you your displacement. The 1/2 a delta t squared, of course, if your velocity isn't changing, a is 0, so that just confirms what I just said. This term would go away, just leaving you this. The 1/2 a delta t squared is how far you would go from rest if your acceleration was a and lasted for time delta t. Now, this is how far you go because you have an initial velocity. This is how much further you would go due to the acceleration. Okay, that's the meaning of the equations, but now let's get back to how we would apply them. And actually, I'm going to separate this into a couple of videos and just, this one talks about the meaning of the equations, where they come from, and so forth, and then we're going to apply it.